Okay, so let's start. So today's topic is the regression versus classification. So as you can see here, there are very well-known two problems for regression and classification in computer vision field. So as you can see left-hand side, this is a single image. Then what you want to do is to estimate the depth information. Depth information or the segmentation label. Sorry, I will rewrite. Depth and segmentation. So, sorry, it doesn't work there. So, what is the difference between the depth estimation and segmentation? So, depth is the relative distance from the viewing from the observer. So, as you can see here, as a human like us, we can easily determine this object is much closer than this object, right? So it's kind of the relative distance, right? So in the depth estimation problem, we want to find out the such a relative distance by using some kind of the machine learning technique or the deep learning technique. What about segmentation? Actually, the semantic segmentation. In semantic segmentation problem, we want to graph the pixels in terms of their semantic meaning. For example, if the bed here, we want to graph the pixels of the bed, something like this, or the what's that? Yeah, table here. We want to graph the pixels of the table object, right? So this is kind of the semantic segmentation problem. Then what is the difference between this regression problem and classification problem? Actually, the solution space of the depth estimation, it's a continuous space. So for each pixel, okay, let's say this is the pixel P, then solution space of depth is the continuous space, something like this. So it seems like it's like the 0 meter or the 10 meter, something like that. So it's like the continuous value. What about the segmentation map? So it's kind of the categorical variable. For example, we want to find out the I'll say 20 class label. In that case, the output of this semantic segmentation map is like the discrete value, something like this, right? So this is the main difference between the regression problem and classification problem. So in the first part of this today's class, we will understand what the regression problem is, and then we will move to the classification problem. Okay, so let me start with the regression problem. Then what is the regression problem? What is the regression problem? So okay, we can start from the predicting a house prices. So yeah, let's see this example. Okay, let's say we have a size of the house here, and we have a price of the house here, right? So let's say this is a training data set. Then we can plot this kind of the samples on this graph, this 2D space, right? So each samples represent each training sample, right? So in here, we want to answer the following question. The first one is what is the relationship between the size of the house and the price of the house? So for example, when you think about this sample, whose size was here and whose price was here, then we want to find out the relationship between the size of price and size of house and price of house. And the second question is, what is the predicted price of the house whose size is about 10,200 to something like that? Then these two kinds of question is the objective of the regression problem. Then what is the regression? The regression is to relate the input variable to the output variable. So as you can see here, let's say our input variable is represented as a xn as a in scalar value, or the vector representation. For example, RT space, something like this. Then we want to relate this input variable to the output variable, defined as a yn in R, just the real space or the scalar value. Then there is two kinds of the goal of the regression problem. The first one is to predict the output for the new input. So this is the first goal of the regression problem. And second goal is to understand the effect of the input of the output. So, for example, if we go back to our previous question, the second question was the prediction problem, and the first question was the understanding problem or the interpretation problem, right? So by using the regression technique, we can understand the effect of the input on the output or the predict the output for the new input. So this is the goal of the regression problem. Then to solve the regression problem or to set the regression problem, we need to build a data set, right? So similar to the other machine learning problem, right? So first of all, the data set, the regression data set, consisting of the xn and yn from n is equal to 1 to the large n, right? Here, yn is the output, and xn is the vector of the d-dimension or the d-dimensional input. So in the training data set, when we're considering the training data set, we have to define what is the input and what is the output. So in regression problem, output must be the continuous value, right? And the number of pairs n is the data set or the size of data or the data set size, and the large T is the dimensionality of the input. For example, if large T is equal to 1, the input data xn or the input variable xn will be just like the scalar value. And if D is larger than 1, xn is going to be some kind of the vector. Okay. Okay, so this is the general setting of the data set. So in machine learning, the input variable or the input data set are also known as the features or the covariate or the independent variable, predictor, something like that. And the output variable, also known as the target label, response, output, or the measured variable, something like that. So first of all, to define or to understand the regression problem, we have to know that what is the input and what is the output in this problem. Okay. So let's say we have a training data set now. Then what do you want to do? So to understand this data set or this training data set, we need to define or we need to find the mapping function. Then what is the mapping function? The mapping function is the kind of the function that approximate the output well enough given input data. So for example, as you can see here, xn is the input variable and yn is the output variable. Then the goal of the regression problem is to find out this mapping function. Sorry for writing. I hope you understand what I mean. Anyway, so f means the mapping function here. So f is a mapping function. Then the objective of this regression problem is to find out the mapping function, right? So in training page, if you remember our previous lecture, in training page, given the training data set, we want to find out our final mapping function by using some kind of the learning algorithm. So it will be the training page, and after training page, we can get the mapping function, and then at testing page, we can estimate the output given input xn, which should be similar to the ground truth output. So this is our goal, right? So this is the mapping function of the regression problem. Okay, so let me start with a very simple example. So if we just think about the one input dimension, in case xn is just in scalar space or just a real space, then we get the very simple linear regression function, mapping function, defined like this one, right? In here, yn is the output variable and xn is input variable, and f is the mapping function. Then we can define this mapping function with a few parameter. For example, something like the w. If you think about the simple linear regression problem, the w is going to be the w0 and just w1, right? So let's see the example here. Okay, let's say we want to find out the relationship between the height of the height and the weight. Then what do you want to do? We want to find out this straight line. Which approximates well given training data set, right? Then how can I formulate this straight line? We need some kind of the mathematic formulation. We can define this straight line with the two variables, w0 and w1, right? In here, w0 is the intersection between this straight line with the y-axis, and the w1 is going to be some slope of this straight line, right? Then by changing this parameter w0 and w1, we can modify this straight line. Then our goal is to find out the optimal straight line that approximates our training data set well, which will be the training procedure. So in other words, we have to find out okay, let's use this one. Yeah, we have to find out this parameter that will approximate this training data set. Then how can I do that? How can I find out the optimal parameter W0 and W1? To answer this question, oh, by the way, what is that? Someone throw yeah. Okay, let's go ahead. Okay, so then How can you do that? How can you do that? So to answer this question, let's go back to our previous example, predicting house prices. So here we have input variable. Let's say this is the input variable xn, and this is the output variable yn. What we want to do is to find out the mapping function between them, right? Right. So let's consider the simple linear regression mapping function defined as a w1 w0 plus w1 times x1 xn, right? In this case, how can I estimate or how can I guess the value of this parameter? This is the our goal, right? Our goal of the regression problem. So to answer this question, first of all, we have to define the cost function. We have to define the cost function. Then what is the cost function? Here's the idea. So choose the learnable parameter W so that the output of the mapping function is close to the ground truth output. So it's kind of the distance, right? Distance for our training data set. Define something like this. This is our idea. And how can we define this distance? How can we say that estimated FW of X is close to ground truth Y? How can we measure this? To answer this question, we need the kinds of the distance function or the kinds of the norm or the kinds of the measure. So for example, so let's say we have a training data set consisting of the big sample, something like this one, this one, this one, this one, this one, and this one, right? So each sample represents the x1, y1 or xn, yn, right? Then how can we define the distance between the ground truth and ground truth output and estimated output? First of all, when we drew some straight line here, which might be our mapping function, something like that, then we can compute the distance between real value and estimated one. So it will be the distance or error, right? Distance or error. Then how can I define this one? We can define this error as some kind of the difference between estimated one with the ground truth one, right? We can define something like this. Then by considering the every possible samples and aggregating them, something like this one, we can define this kind of equation, right? Then our goal is to find out the mapping parameter W that listed here that minimizes this cost, this equation, right? This distance, right? Then here, if we define this kind of the distance measure, okay, distance measure. Generally, let's say C over error, something like this. We can say that this is a cost function. cost function. Then from here, what I want to do is to find out the optimal parameter W, that minimize that make this loss function minimum. So it can be represented in this equation, right? So this procedure is called optimization process. Okay, so this is a general idea. Then how can we define the cost function? Which cost function is best? So we have to think about this one. So people keep going. Let's define this cost function in the formal definition. So the cost function, which is also called the energy function, where the energy or the loss function, where the training objective is used to train the parameter W that explain the data well. Like this, then this cost function quantifies how well our model, for example, FW of X, right? Actually, just parameter W, right? Because just a parameter W determine the mapping function, right? So the cost function quantifies how well our model explains the data, or in other words, how costly our mistake are. How costly our mistake are. So our mistake was output of the mapping function with difference of the output of mapping function with the ground truth label, right? So it will be our mistake. Okay, so this is the definition of a cost function. Okay, so then, okay, so people keep going. Let's summarize what we've done so far. So to solve the regression problem, first of all, we need a training data set, right? The training data set was something like X and Y n, when n is equal to 1 to the large n, something like this, right? So this is training data. So first of all, we have to define the model or the mapping function, and then let's define which parameter should be trained. In this case, the W0 and W1. Then we have to define the cost function, something like this, right? Then our final goal is to find this learnable parameter W, this optimal parameter W that make this loss function minimum. So which will be the optimization process, right? Yeah. So how can we do that? How can we optimize this function? How can we solve this problem given this whole process, this whole data? How can we solve this one? This is our main concern. How can we solve this? So to understand this process, I would like to show you some very intuitive example. But people keep going. Is there any questions so far? So if you have a question, please turn on your microphone or just chat on our chatting room. Okay? 이게 한국말로 잠깐만 할게요. 지금 이게 싱크가 안 맞는 것 같은데 제가 1시간 후에, 그러니까 다음 시간 때는 다시 연결할게요. 근데 지금 좀 글씨가 좀 개판인데 혹시 못 알아들으시는 부분이 있으면 저한테 알려주시면 제가 다시 쓸게요. 알았죠? 네. Okay, so let's keep going. How can I find out the optimal parameter W? they want to solve, right? So people to understand this one, let's see this example. Here we have a training sample, something like this. Training sample. Then first of all, we can approximate our mapping function fwx as a w0 plus w1 times x, right? So in this case, let's say the w0 is going to 50 and w1 is 0.06, right? Which make the straight line something like this one, right? Then we can measure the distance between the ground truth y and estimated one, right? So for example, for each pixel or for each samples, we can measure the distance, right? For example, like en is equal to fw x minus yn, right? We can measure these kinds of the errors for each pixel. Then to determine our loss function, we have to aggregate, or we have to summation. We have to sum the every whole this distance between the estimated one ground truth one. Then we can draw this kind of the loss function with respect to the W0 and W1, because we have to find out the W0 and W1 simultaneously, right? So to draw this one, W0 and W1, let's say in this case, when W0 is 50 and W1 is 0.06, then we can compute the loss value, maybe here. I don't know exactly, but maybe some value, right? Then as bearing the W0 and W1, for example, right, this grid, we can find some loss function with respect to this one. Then it will be something like curve, like this one, right? No, it's not a curve. It's just like the surface, right? So I don't know how can I draw this, but yeah, let's say surface, right? It may be it's going to be surface, right? So if we draw this one again, it looks like this. So here, this is our loss function. Okay, let's say loss function, and this is the this W0 and W1 is a two runnable parameter, right? So as bearing the W0 and W1, we can determine the loss function. For example, let's say W0 is going to be 15, W1 going to be -5, right? So in this case, the value of this one will be -15 and -5, right? So this is the cost curve, right? So from this cost curve, we can understand which point is optimum, which point is minimum, right? So if we redraw this loss function in 2D space, we can say that this is contour flat. So it's going to be looks like this, right? It's just a projection to the 2D space. So in here, it's going to be W0 and W1, right? This red color represent the large loss values, and this blue color represent the small loss value. So what we want to do? What we want to do is to find out the optimal parameter W0 and W1 that generate the smallest loss values in this cost control. Okay, so how can we do that? First of all, if we just choose the one sample here, you determine some mapping function, something like this. So in this example, W0 is going to be 815, and W1 is going to be what? Negative 0.15, right? Something like that. Then in this case, the mapping function looks like 815 minus 0.15x, something like this. So the mapping function looks like that. From here, we can measure the distance between the ground truth values and the estimated values, then which determine this loss value. Okay. Loss values. Okay. Then similarly, by changing this parameter W0 and W1, we can do similar things. Let's say this point moved to here, right? When we see this contour plot, the loss values at this point might be lower than previous point, right? So as you can see here, comparing to this case have a smaller errors than the previous one, right? And what about this point? It seems like this straight line approximated well this given data set, something like this, comparing to this one, but it's not optimal, right? This error, the summation of the error, which may be the which is the loss value at this point, might be similar to this one, right? Because this is the similar point, right? What about this? When I choose the W0 as a, I don't know exactly, but maybe 10, and W1 is going to be 0.11, something like that, then you can make our new mapping function 10 plus 0.11x, something like that. So in this case, when we check this one, the errors with this straight line look like the minimum, right? Comparing to the previous candidate, right? So in this case, as you can see here as well, we can say that this point is minimum point, this value, which was the W0 is going to W0 is equal to 10 and W1 is equal to 0.11. Then we can say that this is the minimum, this is the optimal value, optimal parameter. Then we can say that this optimal parameter make our loss function minimum. So this is our goal, right? Right. So this is the general procedure of the optimization. So people keep going, we have to define the cost function. Before this slide, we just considering the, where is that? Yeah, this one. We just considering the what is that? Yeah, square of the errors, right? So in this case, we just compute the square of the error, right? But there are several kinds of the variant of this cost function. First of all, our previous cost function is called the mean square error, right? Mean means average, and square error is the square of the error, right? So which is one of the most popular cost function, defined something like this. And here xn is the input variable, and output is yn is the output variable, and this term is just our error, estimation error, right? Then we can just aggregate the square error by dividing the sum normalization term. So this is the definition of the MSV cost function, which is one of the most popularly used one. Another example is the mean absolute error, or just called the MAE. The main difference is the MAE is that it just measures the absolute error, absolute distance of this error. This error. Then we can draw these two kinds of the cost function in here. First of all, let's think about the EN error and as an x-axis, and loss or cost as a y-axis, right? So for example, some kind of the function with respect to the error, right? So when you think about the MSC loss, the shape of this one looks like this, right? This is MSC. What about the MAE? What about MAE? It looks like this one, right? This program is the MAE, right? So these two kinds of the cost function are popularly used in the machine learning field, even in deep learning field. So why? Why these two cost functions are widely used? Because they are simple. Because they are simple. That's the reason. So people, you can understand this property first. So actually, there are desirable property of the cost function. The first one is the when target y is the real value, it is often desirable that the cost is symmetry around the zero, something like here, right? It is symmetry across the y-axis, right? Why? Because since the both positive and negative error should be penalized equally. So what does it mean? Let's think about the simple case. So let's say here are training samples here. Training sample, and let's say we have a estimated mapping function here, FWX, right? And let's say we have a training data, one training sample here and another training sample here, right? And let's suppose distance between these two samples are same. So for example, in this case, okay, this is a sample x1 and y1 and x2 and y2. In this case, y1 is equal to error of the second sample, right? No, I will rewrite this one, okay? Okay. So what I want to do is, okay, let's say E1 is equal to FW X1 minus Y1, and E2 of FW X2 minus Y2, right? In this case, at E1 and E2, magnitude of the E1 and E2 would be same, but they might have the different sign. Something like this, for example. So in this case, we want to deal with these two kinds of sample that generate the positive error and negative error equally. So this is our desirable property. So to summarize, the cost function looks like this desirable. Cost function looks like this one. Sorry again. Cost function looks like this one is not desirable. Not desirable. No. Sorry. Okay, so if you remember this figure, the previous two kinds of the loss function satisfies this first properties, right? And the second property is that the cost function should penalize the large mistake and very large mistake similarly. So what does it mean? Okay, so let's see this example again. Let's say we have a training sample, something like this, but we have one more training sample here, right? It might be the outlier. Actually, we don't want to consider this outlier, right? So we just want to approximate the major statistic of the training data set, but this sample is outlier. This sample might be outlier, right? So if the cost function consider the this outlier, that the mapping function, the straight line, will be something like this one, right? Because they considering this error again, this error as well. So it's not optimal. I mean, it's not a desirable, right? Our desirable mapping function should something like this one. So it means that our cost function should penalize the large mistake, something like this one, and the large mistake here, something like this one, and very large mistake, something like this one, similarly or equally, right? So this is the second desirable property of the cost function. But as you can see here, previous cost function, when you think about the large mistake and very large mistake here, they didn't consider these two kinds of errors equally, right? Then how can we satisfy this second property? We can use the loss function, looks like this one. Looks like this, right? In here, if we consider this one, we can equally deal with this error and very large error here. This loss function might be same, right? So this cost function is called the robust cost function. Robust cost function, which will be the which will have the better how to say better performance than previous simple loss function, something like the least square or MSE or MAE case, right? Then the question is, which one is better? Which loss function is better? Or which loss function is the best? The answer is, we don't know. We don't know. Why? Of course, this lowest loss function, this lowest cost function is better than the MSC and MAE, but it demands a high computational complexity to compute the cost values. So you can search this function, but this cost function requires a number of the many operation comparing to the just a simple MSC and MAE, right? So in other words, there are very well-known trade-off between the statistical properties and computational cost. So which loss function is the best? We cannot say that. We cannot say that the lowest cost function is always better than the simple cost function. So it depends on. So it depending on application. But again, due to the simple and easy to compute, the MSC and MAE the most popularly used the cost function. But if you want the better result, if you generate the better result, you can consider the lowest cost function as well. Okay, so this is the desirable property of the cost function. Okay, so now we have a cost function. Then how can we find out the optimal value, optimal parameter W space, optimal parameter W that minimizes this cost function? Then how can we do that? So if you remember our previous example, something like this one, this one, this one, this one, we just considering the whole possible values, right? So in previous, we just compute the cost over the whole values W in a grid, right? For example, let's say the possible W space, which looks like this. Possible W space looks like this. Then we can sample the possible point here in a grid. And then we can just pick the best, right? This is very brute force, but extremely simple, right? We can just search every possible point, but you can easily say that it's not efficient, right? So you can imagine that it has too many for loop, right? To search every possible solution. So resulting in the exponential computational complexity. So it's not an efficient way. So we need a more efficient and effective way to optimize, to solve this problem, right? That's why we need to introduce the gradient descent algorithm. Okay, so what is a gradient descent algorithm? Maybe you can, maybe most of you heard about this gradient descent algorithm, right? Then what is the main idea of the gradient descent algorithm? We can imagine that we are in the mountain and we want to go down the mountain in a very efficient way. Then which direction should we follow? Which direction is the most efficient way to go down the mountain? Okay, let's say we are here. We are here. We can go this way or this way or this way or this way, right? We can easily say that this way is the most efficient way, right? Why? Why this way is the most efficient way? This direction can reduce the loss function most efficiently comparing to the other direction, right? This is the main idea of the gradient descent. Here is the idea. So we can just use the concept of the gradient. Okay, so people keep moving. What is the gradient? What is the gradient? So is there any student from the math department? Okay, let me check. Yeah, right. 경사. 그렇죠? 한국말로 경사. So what's the real meaning of the gradient? Then why we have to considering the gradient? So if you study the machine learning or even deep learning, the gradient descent will be the one of the most popular used optimization, right? So current most optimization are based on the gradient descent algorithm. Actually, not the same, but it's almost method are based on the gradient descent algorithm. So you have to understand this gradient descent algorithm in high level and fine level as well. So in Korean, gradient means like 기울기, and descent means 하강, right? So 이제 한국말로는 기울기가 높은 방향의 반대 방향으로 내려가는 게 제일 아까 옵티멀이라고 했으니까 기울기가 가장 가파른 곳에 반대 방향으로 내려가라 라는 사전적 의미가 되겠죠? 그레디언트 디센트. 네, 그래서 그럼 그레디언트가 무엇이냐? So what is the gradient? So gradient, okay, so I want to show you some example. Okay, so let's think about the 1D example. Okay, so let's say we are here. What is gradient here? So what is the slope? What is the gradient at this point? The meaning of the gradient is the slope of the tangent to the function at the point, right? Which point to the direction of the largest increase of the function. So in this case, okay, let's redraw this one again. So in this case, the slope of the tangent at this point looks like this one, right? So slope, or called the gradient, will be the slope of this tangent line, right? So what is the sign of this one? What is the sign of this tangent line, tangent function? Positive, right? Positive in this case. So it means that at this point we have to move the negative negative way, something like this, to go to the minimum point. Okay, let's say minimum point. So at this point we have to move this direction, right? So it means that the direction of our moving revert to the sign of the gradient, right? So in other words, the direction of the gradient descent is a negative gradient. So for example, here's our cost function with respect to some some parameter W. Then let's say we are here. Let's say we are here. Then to arrive the minimum values, we have to find we have to find the optimal path, right? So to find out the optimal path, we have to determine the direction first. So in this case, we use the negative gradient descent, negative gradient direction to determine the further step, right? So this is the main idea of the gradient descent. So here is the outline. So what you want to do is first start from any initial value. For example, let's say W0 is equal to 1, equal to 0, and W1 is equal to 1, something like this. So this is just called the initialization. And we can keep changing this learnable parameter W to reduce our loss function until we hopefully end up the minimum. So this is main strategy of the gradient descent algorithm. So let's see the example. Here we have a loss function again with respect to the W0 and W1. And let's say we start from this initial state, right? Then there are going to be the three kinds of the question. The first one is, where do we start? And second question is, which direction should we move? Third question is, how much do we move? These three kinds of questions determine the one gradient descent algorithm. Okay, so let's see this example first. So the first question is related to initialization. So as you can see here, the starting point is depending on the initial point or the initial parameter or the initial state, something like this. Then which direction is related to the gradient? Precisely speaking, the negative gradient, right? Negative gradient direction, right? So as you can see here, this is our path. This is our path, and we can follow this path according to the negative gradient direction. So like this. So let's say this is a loss function of the W parameter, right? Then the gradient of this loss function with respect to the W will it's going to determine the direction of our next path, right? Then the last question is, how much do we move? Which is related to the learning rate. So as you can see here, this learning rate determines the magnitude of the movement. So we can move this direction, something like this, or something like this, or very small, something like this, right? So by adjusting this learning rate, we can determine the step size of each iteration, right? So this is the gradient descent algorithm. So let's think about the different example. So let's say we start from here instead of this one. This one is the previous initial state, right? In previous page, right? Then if we start from different initial state, then the optimization path will be looks like this, right? So comparing to this previous path, looks like this. The optimization path with this initial state, this initial parameter looks like this. So what does it mean? Let's suppose we use the same learning rate and same gradient computation method, but different is only the only difference is the initialization step. So it means that initialization is one of the most important issues in the gradient descent or the optimization process, right? So in the deep learning area, maybe in next week, we will talk about how to initialize the optimal parameter. But in here, we just assume that we can randomly pick the initial state, but it is going to be it is going to determine the optimal path, right? So this is the initial statement. Okay, so let's summarize the gradient descent algorithm. So we can make a pseudocode for the gradient descent algorithm as follow. So if you remember this one, first of all, we need to find define the initial parameter value. Let's say W0, right? Which is the W0 0 state and W1 0 state, something like this, right? Then we can iterate this step to pass the to move to the optimal state by using some iteration algorithm. We can implement this one using some kind of the for loop or the while loop, something like that. And this current W0, the current W0 is updated to the next W0 by using this term, right? So this term consisting of the gradient and learning rate here, right? So this gradient determines the direction of the next step, and the learning rate determines the magnitude of the movement, right? So these two terms multiply each other, and this W0 and W1 is the current point, right? So this is optimization in terms of the W0, and the optimization in terms of the W1 is similarly defined, something like this one. The main difference is that we have to compute the loss gradient in terms of the W1 rather than W0 to update the W1. So in this case, this is called the partial gradient, right? Partial gradient. Partial gradient means this loss function is related to the W1 and W0 and W1. So we have to find out the gradient with respect to each variable, right? So this is called the partial gradient. Okay, anyway, so by using this kind of the partial gradient, we can update each parameter W0 and W1. Okay, so by iterating this work procedure, we can convert it to we hopefully convert to the optimal loss values or the optimal point. Okay. So before keep moving, let's think about how to compute the gradient. So if you remember our high school, we used the derivative, right? In Korean, 미분, right? So derivative is to finding out gradient. Right. Gradient. So gradient was the slope of tangent, right? If you remember this page, tangent of the function, right? Then how can we find out the slope of the tangent function? So question again, how to find out the slope of the tangent function? So let's think about this example first. So this is the function of x, right? Then we want to find out the tangent, slope of the tangent. Then, so first method is a numerical gradient method. So the loss function gradient with respect to the x, it's going to be look something like this one, right? X plus h minus fx, right? This is the kind of the way to compute the numerical gradient. So, for example, let's think about our previous example. We have a mapping function, something like w0 plus w1x, right? Then our cost function or our loss function in terms of w is going to be fw x minus y squared. It's going to be w0 plus w1 x minus y squared, right? If we think about this case, we can compute numerical gradient of this loss function, something like this one, h l w plus h minus lw, right? So in this case, h might be very small value, for example 0.0001, and in here w is the current parameter, right? Then by using this kind of computation, we can answer the gradient at this point, right? So this is called the numerical gradient, something like this one here, this one is here, right? So by using this numerical gradient, we can optimize our parameter as well, but actually it's not optimal, right? It's just approximation, and it's very slow, right? So we need another way to compute the gradient. That's why we introduced the analytic gradient here. So analytic gradient. So what is the analytic gradient? So in analytic gradient, we define the analytic gradient in previously, something like this. So for example, if we think about this this learning procedure, the loss gradient with respect to w is going to be what? 2 w0 plus w1 y minus x, right? X minus y times 1 or x when w0 and w1, right? So from here, we can first define the analytic gradient and then just to use this analytic gradient to optimize our network parameter or our machine learning parameter, right? So to summarize, the numerical gradient is simple, but it's very hard to approximate the real gradient. So we need to analytic gradient first for our loss function, and then we can update our network, our parameter w by using this analytic gradient. It will be much easier to, it will be much accurate. Okay, so that's the way to compute the gradient. Okay, so is there any problem so far? 네, 기본적으로 저희가 사실 로스 펑션, 코스트 펑션은 혼용해서 사용을 합니다. 네. Any other question so far? 행렬같이 적은 부분이? 행렬같이 적은 부분이 어디죠? 이 부분? You mean the right bottom side? 아, 이게 이게 오늘 아이패드가 좀 이상한데? 잠시만요. 이게 무슨 얘기냐면은 이제 우리가 로스를 W0에 대해서 미분을 해야 되고 W1에 대해서도 미분을 해야 되는 거잖아요. 그래서 사실 이 그레디언트는 W0 버전이 있을 거고 W1 버전이 있을 거예요. 왜냐면 이게 파셜 그레디언트니까. 왜냐면 그쵸? 잠시만요. 네. 그래서 요 펑션을 요 펑션을 W1에 대해서 미분하면 2W0 플러스 W1 X 마이너스 Y가 끝이겠죠? 그쵸? W1 타임스 1이니까. 근데 이걸 W1에 대해 미분하면 W0 플러스 Y1 X 마이너스 Y 타임스 X는 되겠죠. 왜냐면 X 텀이 여기 있으니까. Y1에 연결되어 있으니까. 이제 이 두 개가 이렇게 달라진다는 걸 아까 그런 식으로 표현을 한 겁니다. Okay, I will try that. Okay, so any question? Okay, so if not, let's take a 10-minute break and let's see again. 그 어제 학부 수업할 땐 잘 되는데 이게 갑자기 안 되는데 제가 다음 시간에 다시 한번 체크를 해볼게요. 근데 오늘은 일단 시간이 없으니까 이 세팅으로 하겠습니다. 그래서 조금 더 속도를 내야 되는데 조금 더 천천히 필기를 하고 다 못 끝내면 다음 시간에 더 하는 걸로 하겠습니다. 오케이? So, 잠깐만요. 다시 공유를. Okay, so let's continue. Actually, I was going to finish this material until last page, but I'm not sure I can finish today. But let's try. So anyway, so the analytic gradient is in most gradient descent method use the analytic gradient because they are accurate and easy to compute. Okay, so there are few kinds of the property. By the way, someone is there anyone who turn off your microphone? 혹시 지금 뭐 마이크 켜신 분이 있는 것 같은데 좀 켜주실래요? 혹시 같은 연구실에 있으신 분이나 말을 좀 해주세요. 제가 찾아볼게요. 아, 제가 끌 수가 있네요. 잠시만요. 네, 됐습니다. Okay, so let's continue. So, and then there is a few kinds of property of the gradient descent. First thing is the sign of the gradient. Okay, let's think about this example. Okay, so let's say we have a loss function, looks like this one, and looks like this one. Then let's think about the sign of the gradient here. Okay, so let's say we are here, right? Then if you remember previous slide, if you remember this slide, the gradient at this point is the slope of this tangent line, right? So in this case, the gradient of the loss function with respect to the W1 is positive value, right? Positive value, like this, right? So in this case, we have to move the left-hand side because of this negative this minus term, right? So we can move something like this one, right? So it means that by following this low cost function, we can converge it to the minimum value, right? Then what about the second case? So if we are here, the tangent of this function looks like this one, right? So in this case, the loss gradient with respect to the W1 is negative, right? So in this case, the current parameter point move to the right-hand side, something like this one. So we can follow the path, something like this, until our gradient descent method to come end at the minimum, right? So this is the property depending on the sign of the gradient. And what about the learning rate? Learning rate. So learning rate determine the step size of each iteration. So let's think about this case again. This is a loss function, of course. So let's say we are here and here. What about if we use the very small alpha value? Then of course we can move to this way, right? But it might be very slow, right? Something like this one. So in this case, the gradient descent can be really slow. Then what about another case when alpha is too large? So in that case, the gradient descent can overshoot the minimum. What does it mean? The next step of the gradient descent will be something like this, right? It might overshoot the minimum because the minimum is here, right? Then the next step will be something like this, right? Or this one, something like that. So in that case, it may fail to converge, even diverge, right? So from here, we can say that optimal learning rate is one of the most important issues in the gradient descent, right? So Alt M이 뭐죠? 혹시 형준 학생 Alt M을 왜 눌러야 돼요?
교수님 말고 전부 다 음소거하려면은 Alt M을 누르라는 뜻입니다.
예. 알겠습니다. 감사합니다. 네. Okay, so let's keep continue. So okay, so if you remember this slide, so initialization is really important, and learning rate is another important issue in the gradient descent algorithm. So in here, we just skip these kinds of things, but in the deep learning part or deep learning lecture, we will talk about how to determine optimal learning rate or the optimal initialization. Okay, so then what is the limitation of the gradient descent? Actually, there are so many limitations, right? So that's why there are so many variants nowadays, but I want to introduce the very well-known limitation of the gradient descent. So let's say we have a loss function looks like this. So actually, in here, the loss graph is really beautiful, right? So it's just a convex function, but in the case, it's non-convex case. It's non-convex. Non-convex means the final loss function with respect to the W1, it's not a convex anymore. So why this effect happen? There are two kinds of reasons. The first reason that in generally we do not use the linear mapping function anymore. Actually, if we considering the deep learning area, the most parameters combined in a nonlinear setting. So kind of nonlinear mapping function. Another reason is that the due to the cost function. Of course, the MSC or the MAE generate the convex loss function, but when you think about the another cost function, that might generate some such kind of the cost function. So in that case, it is really hard to optimize by using the vanilla gradient descent algorithm. Let's take a example here. So let's say that this part is real optimal or global optimal. Global optimum. We have to converge it to this point, right? Then what if we are here? What if we are here? First of all, we have to compute the gradient, right? So to compute the gradient, we can find out the tangent line, tangent function here. But as you can see here, the slope of this tangent line will be 0. In other words, the W1, the loss gradient with respect to W1 is going to be 0, right? So in this case, the one step in the gradient descent will be 0. Then the W1 is remain unchanged, right? So in this case, we cannot move to the optimal parameter values because we are get stuck to the local minimum. Let's say this is a local minimum. Local minimum. This is one limitation of the gradient descent. And another limitation here. Okay, let's suppose that we are here. Actually, we want to move to this way, right? But if we just use the vanilla gradient descent, the direction move to this way, right? Because the tangent line is here, and the sign of the tangent line is negative, so positive, right? So we have to move to negative direction. So we might move to here, not this direction. So we will get stuck to the local minimum as well. So that's the limitation of the gradient descent algorithm. Okay. So yeah. So far, we've talked about the single feature case, right? So single feature or the single variable means we just considering the input, scalar input and scalar output. That, but if you think about the house price prediction problem again, the price of the house is not only depending on the size of the house, right? The number of bathroom or the number of floor or the age of a house will define or will impact on the house price as well. So to accurately regress this training data set, we need more data. No, I mean we need more features per each sample. Here are some examples. So in here, to regress the price of the house, we can now considering the several kinds of the features. Let's say feature. In Korean, 특징. So each input can be represented in a vector form. So for example, this one related to size, and this value related to the number of bathroom, this one related to age of the house, something like this, right? So we can extend our previous example to this general multiple variable cases, right? Okay, then the mapping function, our previous mapping function, which was defined something like this with the W0 and W1, then we can generalize this previous simple linear regression mapping function as like this, right? So now we have four feature values, right? xn1, xn2, and xn3, and xn4, like here, right? So now from here we can use this multivariable mapping function case. For example, our mapping function will looks like this. So the number of parameters that we have to optimize would be much higher than the previous example. In previous example, the number of parameter was the 2, right? But in this case, the number of the learnable parameters are 5, right? Because here, right? It means that our loss function is defined in a six-dimensional case. You can imagine. So if you remember this curve, this loss curve, it was defined in a 3D space, right? But if we consider this multivariate case, the loss function will be 6D defined in a 6D space. So it's not possible. It's not possible to draw, or it's not possible to imagine, right? But fortunately, we already have the very good mathematic tools to optimize this parameter. So mapping functions are defined here. So for convenient notation, we usually define the x and 0 as a 1. So this term is related to bias in the deep learning area. Anyway, then our input feature vector will be looks like this, which is defined in the R large T plus 1 space, and the learnable parameter W is also defined R large T plus 1 space, right? So in this case, we can simply represent our mapping function, something like this one, W transpose Xn. So this is the dot product, right? Dot product W vector W is W1, W0, W1, W T times X0, X1, Xt, right? So this is the vector notation of this mapping function, right? So from here, we can call this mapping function as a multivariable linear regression problem. So from here, we can consider the multivariate linear regression problem. Okay, so if you remember the gradient descent for the single variable case, it was something like this, right? But if we consider the multi-variable case, it looks similar, but it defined for each samples I is equal to from 0 to what? T, right? Large D, the dimensionality of the input space, right? So the one step is looks like this, right? So we have to compute the loss learning rate times the gradient with respect to the Wi, right? Then if you considering this loss function, the simple MSE loss function, we can compute the gradient with respect to the Wi. So this one was something like W0 plus W1 x1 W2 plus W times x2 blah 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 W t xt, right? Then if we compute the analytic gradient of the this loss function, it looks like this with one more term, right? This term from here, right? So I strongly suggest to you to solve this one by yourself. It is related to the chain rule. Okay, so this is the gradient descent for the multivariable. Okay, so this is the end of the regression problem. Then from here, we would like to move to the classification problem. But if you fully understand what is the regression and what is the loss function and what is the gradient descent algorithm, you can easily understand the classification as well. You can just to find out the main difference between the regression problem and classification problem in a mapping function and mapping function. So let's find out that. First of all, Similar to the regression problem, the classification problem relates the input variable x to the output variable y, but y can only take a discrete value or categorical variable. What is a categorical variable? So here's an example. So in some application, we would like to classify the spam mail or the non-spam email, or fraudulent or not, or the malignant or the benign. 뭐죠? 이게 그 암 맞죠? 네. 종양이냐 아니냐 그 두 개 클래스인 거죠? 그 클래스 또는 yeah. So in some application, we would like to classify each sample to the discrete or the categorical class, a categorical variable. So if we think about this last example, there are two possible output, negative class or the positive class. So it means that y is in the discrete space 0 or 1. Okay. Then how can you solve this one? How can you solve this one? Let's think about this example first. Similar to the regression problem, we have a training data, right? So tumor size is x, malignant, the decision of the malignant is y, right? Here are some training data set. Let's say x1, y1, something like this. Then, similar to the regression problem, we can find out the mapping function. We can find out the linear mapping function, something like this one, that approximate this training data well, or like this one. But as you can see here, in classification problem, we want to classify the samples to the discrete label. We don't want to find out the continuous value, right? So to solve the classification problem, we need a new mapping function or new way to generate the categorical output. So here's a solution. First of all, we only considering this 1 over 0. First of all, we can normalize the output of the mapping function between 0 and 1, right? And then we can just threshold that values at 0.5. So what does it mean? So let's say if we normalize the mapping function with some kind of the technique, then we can determine if the mapping function is larger than 0.5, predict the y is equal to 1, or the positive class. Or if the mapping function is smaller than the 0.5, predict y is equal to 0. So this will be our new strategy to classify these classification samples. Let's see in detail. So the first of all, how can it normalize? And how can it threshold? So first of all, we want to make the output of this mapping function within 0 and 1, right? Then how can you do that? So if you remember the regression problem, the output of the mapping function can be any continuous value, right? But in this case, we want to make this output within from the 0 to 1. So to do this, we introduce the new function, something like this. The shape of this z function is something like this. Okay. So if we use this kind of the nonlinear function, then we can make the output of the we can make an output of the mapping function within 0 and 1, right? Something like this. Something like this one, right? Right? So we can rewrite our mapping function, something like this one. So if you remember the mapping function in linear regression, it was just like this one, but comparing to this one, now we have a nonlinear term in here, right? Actually, this one is called sigmoid function or the logistic function. This one. So in this case, the W transpose times X will determine the output of this mapping function. So, for example, W transpose times X is larger than 0, this part. Then Fx is X. F of X is larger than the 0.5 as well. Then we can say that this is the positive class. And if the W transpose X is smaller than 0 here, then the F of X is smaller than the 0.5 here, then Y is going to be 0, right? So this is two kinds of the rule to find out, to determine the class of the label. So in here, we can say that the mapping function for the classification is the kind of the probability that Y is equal to 1 on input X, right? We can rewrite this mapping function something like this one. We can read this mapping function as a probability that Y is equal to 1 given X parameterized by W, right? This is a new mapping function for the classification problem. For example, if you think about the two class classification problem, the sum of the probability should be 0. Should be 1, right? For example, the probability of the Y is equal to 1, Y is equal to 0, and probability of Y is equal to 1 should be some of them should be 1, right? Or this relationship. So for example, okay, so if we have the feature vector x0 and x1, and x1 is the tumor size, and the output of the mapping function was the 0.7, then we can say that this pattern have a 70% chance of the tumor being malignant, right? Or this pattern have the 30% chance of the tumor being non-malignant, right? So by using this output of the mapping function, we can determine the probability that Y is equal to 1. Okay, so is there any question so far? If not, let's continue. So in the classification problem, we need to introduce the decision boundary concept. So what is the decision boundary? So here's the example. Okay, let's say we have two input features, x0, x1, and x2, right? And we have a two class, circle class and how to say x class, right? And what we want to do is to find out the mapping function that classify these samples. Maybe looks like this, right? This is called the decision boundary. in classification problem. Decision boundary in classification problem. Then, how can I find this decision boundary? It is a similar procedure to compute the runnable parameter W in the regression problem. How can we do that? So first of all, this is our mapping function, right? That was the nonlinear mapping. Was something like this, right? G, right? Then it means that the shape of this one, it looks like this, right? Let's say this part is K, in terms of K and GK. Then we can say that K is larger than 0, GK, G of K should be larger than 0.5, or if K is smaller than 0, then GK, G of K is also smaller than the 0.5, right? So in other words, if the optimal parameter W0 is equal to -3, W1 is equal to 1, W2 is equal to 1 as well. -3, 1 as well. K is equal to K is larger than 0 will be -3 plus x1 plus x2 is larger than 0, right? Then this one can be rewritten something like this one, right? So in here, this inequality represents this part, right? In reverse case, this function, this inequality represents this part, right? In here, this decision boundary determined by W0, W1, and W2. In this case, -3, -1, -3 plus 1 plus 1, right? So to summarize, decision boundary is determined by the runnable parameter W, similar to the regression problem. Okay, so this is the concept of the decision boundary. But comparing to the this case is really challenging case, right? As you can see here, it is really hard to find out the straight line that that classify this sample properly, right? So any straight line cannot classify these samples well, right? Maybe the optimal decision boundary will be looks like this one, maybe optimal. But if we consider the linear function, if we consider only linear function similar to this one, we cannot find out the decision boundary, something like this. So if we considering the non-linear term, then if W0 is equal to -1, W1 is 0, and W2 is 0, and W3 is equal to 1, W4 is equal to 1, we can define the new criteria to classify the samples, something like this. In that case, the decision boundary is going to be circle defined by W1 square plus x1 square plus x2 square is equal to 1, right? So in other words, by introducing the nonlinear term in the mapping function, we can also find out the nonlinear decision boundary. Okay, so let's summarize the logistic regression. We have training data set x1 and x1 and y1, x2 and y2, blah blah blah, xn and yn. Nth sample is considered consisting of the vector xn, right, in the large T plus 1 space, and yn is the categorical variable, right? And here we can introduce a new mapping function with a nonlinear term. Then the question is how to find or how to choose the optimal parameter W similar to the linear regression or the regression problem. This is the same objective, right? So first of all, we have to determine the cost function as well, similar to the regression problem. So very simple possible cost function is the mean square error, right? So if you remember the mean square error in the regression problem, it looks like this, right? So this is the output of the mapping function, and this yn is the ground truth label map, right? They are aggregated across the every possible samples, right? Something like this. But in the regression problem, the cost function of the MSE was the convex. Looks like this, if you remember the previous slide, right? But in here, now we have some nonlinear term. Something like this, right? So this loss function with respect to the W is not a linear mapping relationship anymore. This is a nonlinear mapping relationship. Nonlinear mapping relationship, right? So in this case, the cost curve looks like this one. So in that case, if we are here, it will be really hard to converge it to the optimal point by using the gradient descent algorithm, right? So it might be very unstable, right? Because this nonlinear mapping relationship. So using a mean square error loss function in classification problem, it's not an optimal way. Then which function is better? Which loss function is better? We need to define another mapping function to solve that problem. So here is a new loss function for the logistic regression. So let's think about the property first. Okay, we already know this fw of x is defined from 0 to 1. We already know that, right? Then the desirable property is that when if yn is equal to 1, the output of the mapping function also should be 1, right? Because okay. So when yn is equal to 1 and the mapping function, the output of the mapping function is equal to 1, that cost should be 0, right? So in other words, if the output of the mapping function is going to 0, then cost function should be maximum, right? So the question is which cost function satisfy this property? The cost function looks like this one, right? So this log graph satisfying this shape. Okay, so actually the log graph, negative log graph is looks like this, right? So you can easily draw this one. So in other words, if the mapping function is to 0, maybe here, then but y is equal to 1, then this prediction is not correct, right? So in that case, we have to penalize the learning algorithm by very large cost, maybe here, right? So this cost function is used in the y is equal to 1 case. Another case, yn is equal to 1, the desirable properties should be reverse, right? So comparing to this one, the shape of the cost function, and then this. Right. So you can throw this cost function yourself and understand why this term is used to define the yn is equal to 1 case, yn is equal to 0 case. Okay. Anyway, this is the new cost function for the logistic regression problem. So to summarize the cost function for logistic regression problem, it looks like this. So our loss function is like this one. This cost term is defined two equation, defined with the two equation. First case is yn is equal to 1, and second case is yn equal to 0, right? So, and we already know that yn is equal to 1 or yn is equal to 0 and yn is equal to 1 always, right? Then we can rewrite this cost function in a one equation, right? One equation. So this function is our cost function for logistic regression problem. Okay. Then how can we optimize this one? How can we optimize this one? Of course, we can use the gradient descent defined in the linear regression part, right? Okay, the problem setting is something like this. We have a cost function here, right? Defined the previous slide. And our goal is something like this. We want to find out the runnable parameter W that minimizes this loss function, right? Then we can use the gradient descent similarly, right? The one step of the gradient descent, it looks like this, right? And then we can compute the loss gradient with respect to the Wi from here. Looks like this one. So you will be also homework. You can derive this one yourself. Anyway, if you derive the derivative of this loss function, one step is going to be something like this, right? So what is that? So if you remember the gradient descent in multivariable case, okay, let's go back to the previous one. Here, output of this part is exactly the same, right? This part is exactly the same. Same to regression problem, right? Then what is different? What is different between the one step in regression problem and the logistic regression problem? The equation is the same, right? The main difference are here, right? In linear regression problem, the mapping function was W transpose times X, but in here, it's a nonlinear case, right? Right. So main difference are here, but the one step is exactly the same to linear regression case. Okay. Okay. So far we've talked about the classification problem, right? Then so far we're just considering the two-class classification problem, right? But in real world or in real application, there are so many possibility that requiring the multi-class classification problem. For example, email tagging problem. Email tagging class will be might be the word, brand, family, hobby, something like that. And weather, in case of weather, the sunny, cloudy, rain, snow, it's going to be the possible class, right? So in this case, we cannot classify these samples, the training samples, by using our previous approaches, right? So we need another way to solve this multi-class classification problem. So here's the example. This is the binary classification problem, and this is a multi-class classification problem. And in binary classification problem, the decision boundary was something like this one. Then in multi-class classification problem, how can I define the decision boundary that describes this one? So here's the idea. First of all, the multi-class classification problem can be decomposed to the several multiple sub-problem, right? So if we consider this class, the remaining other class will be the just negative class, right? Something like this one. If we consider this class, this whole samples will be the negative, right? If we consider this one, this part will be the negative class, right? In that problem setting, each problem can be solved by the linear two-class logistic regression problem, something like this one, and this one, right? So this decision boundary define something like this, or second decision boundaries are here, and third decision boundaries are here, right? And then after training these three kinds of the parameter independently, we can determine which class let's say, okay, so the probability of the which class generate the largest smallest loss value, right? So in other words, given a single input here, we can compute the three kinds of mapping value of the mapping function, something like this, right? Then we can just pick this value if this value is the maximum, right? Yeah, it's going to be maximum, right? Because we considering the probability case, right? So it should be maximum anyway. So if this class is maximum, the that is equal to 2, right? So in this case, we can say that this given X sample should have the second class. So that's the way to solve the multi-class classification problem. Okay, so this is the end of today's lecture. Do you have any questions so far? Okay, there is a question. Okay, remember the introduction section in terms of quiz. 제가 수업 시간에 이제 앞으로 그 숙제 손으로 해보라고 이제 많이 내줄 건데, 왜냐면 제가 이제 정해 시간에 다 풀지 못하니까 그런 부분들은 혼자 해보시면 돼요. 혼자 해보시면 되고, 뭐 답을 알고 싶으면 저한테 따로 연락해도 되지만 기본적으로 제출하는 숙제는 아닙니다. 두 번째 질문이 36차. Okay, so let's rewrite this part. So this form will be W0 plus W1 X1 plus blah 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 Xn Wn X Ni. No. Wi Xni plus blah 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 X Wt Xnt minus y squared, right? Then we can find the derivative of this term in terms of the xi, for example. Then it will be something like this term again, and this xni should be here by the chain rule, right? So it's going to be this term. Okay. 이해가 되셨나요? 네, 알겠습니다. So, is there any other question? So, if not, let's finish. Let's finish this lecture, and next week we will talk about the learning theory, like the legalization or the bias or bias, something like that, and then start to introduction of the deep learning. Okay. Thank you very much. So if you have any question, please let me know. If not, let's finish.